Welcome to The Explainer. Today we are decoding the ultimate black box, artificial intelligence. We've all seen AI do absolutely incredible things lately. But think about this. When an AI makes a massive, life-altering decision, like diagnosing a critical medical condition or flat-out denying your bank loan, how do we actually know why it made that choice? It's a huge transparency problem. Well, today I am incredibly excited to walk you through a brilliant new framework from a 2026 IEEE paper. It essentially uses AI to fact-check AI, making sure that machine decisions aren't just easy to read, but actually honest.
Here is our roadmap for today. We're going to cover the AI transparency problem, when LLMs hallucinate, the two-stage solution, the iterative refeed loop, testing the framework, and finally, what a trustworthy AI future looks like. Let's get right into it.
Okay, let's dive into Section 1, the AI transparency problem, and peek inside the black box.
So to solve this black box issue, data scientists use a field called explainable AI, or XAI. The whole goal of XAI is to pull back the curtain and show us exactly which data points convince the AI to make its prediction. And in high-stakes fields like healthcare or finance, translating these decisions accurately is literally a fundamental requirement. But there's a catch. The raw outputs from XAI can be incredibly confusing. Take a look at these examples. On one side, you have a SHAP bar chart loaded with abstract codes like WKHP and numbers pointing every which way. On the other side, there's a GradCam++ heat map that frankly looks like a blurry, colorful weather radar. Now, these are brilliantly clear, assuming you have a PhD in data science, but for a doctor looking at a patient's chart or a regular person trying to figure out why their mortgage was denied, these visuals are completely inaccessible. They are technically transparent, sure, but practically useless to the everyday user.
So that begs a pretty massive question. How do we translate this highly technical data for everyone else? Well, recently, the tech world has turned to large language models, the exact same technology behind your favorite AI chatbots, to act as these eager translators. We just feed them the complex heat maps and charts and ask them to write a nice, simple, human-readable summary. Sounds like the perfect solution, right? Well, it turns out relying on a single AI to translate another AI introduces a brand new massive danger.
Which brings us to Section 2, when LLMs hallucinate explanations. This is the false translator problem. Let's clearly define the threat we're dealing with here. A hallucination in this context isn't just the AI getting a little confused. Oh no, it's the AI generating a totally fluent, highly confident, but fundamentally false narrative about how the original AI made its decision. Just imagine an AI telling a doctor that a patient is completely healthy because of their blood pressure when the actual raw data showed the model was really looking at their cholesterol. If an unverified hallucination like that gets sent to an end user, it would completely destroy trust in the entire system.
The researchers in this 2026 study actually mapped out the specific crimes these explainer LLMs commit. It's quite a rap sheet. We're talking about omissions of key features, where the AI just completely drops vital data points. Then you have factual drifts, where the AI simply wanders away from what the numbers actually say. Sometimes they do swapped importance rankings, claiming feature A was the biggest factor when it was actually feature B. And worst of all, unsupported causal claims, where the AI just flat out invents a logical reason that simply isn't in the data at all.
So, how do we fix the rogue translator? Let's check out Section 3, a two-stage LLM solution. Meet the translator and the editor.
This beautifully illustrates the full two-stage meta-verification architecture. Over on the first stage, you have the explainer LLM. Its only job is to take the raw XAI outputs and draft a natural language explanation. But, and this is the crucial part, instead of sending that draft straight to the user, it gets passed to Stage 2, the Verifier LLM. This second AI acts as a totally impartial, super strict critic. It checks the draft against the raw data, and if it finds even a single error, it rejects it and forces the explainer to try again.
Let's break that dense diagram down into 3 really straightforward steps. Step 1. The explainer translates using something called zero-shot chain of thought. Now, this is just a clever prompting trick where the AI is told, hey, let's think step by step, which forces it to actually write out its reasoning before giving an answer. Step 2. The verifier checks this draft using meta-prompting, basically a highly structured set of rules used to evaluate logical coherence and catch those sneaky hallucinations. And step 3, if the draft fails, it enters a refeed loop for targeted revision.
And that flows perfectly into Section 4, the iterative refeed loop. Think of it as the hero's journey of an explanation.
Now, what's really fascinating is seeing this loop in action. Here's a visual example straight from the paper. The AI is tasked with explaining why the system identified a specific image as a cat. So the explainer drafts its first attempt, and it completely hallucinates. It claims that the bottom right region, which corresponds to the cat's paws, was highly relevant to the prediction. But if you actually look at the raw heat map data, there's absolutely no activation on the paws. The AI only looked at the cat's face and ears.
But because of this framework, the verifier catches the mistake instantly. Let me read you the exact verbatim feedback that the strict editor AI gave back to the translator AI. Erroneously assigns relevance to the bottom right region. This constitutes an insert hallucination error and triggers a mandatory refeed. I mean, how incredible is that? We are literally looking under the hood at an AI evaluating another AI. Using these dynamic prompt fields, the verifier forces the explainer to confront its mistake and generate a newly corrected draft that actually aligns with the real data.
But does this work consistently out in the wild? Let's move to Section 5. Testing the framework and proving the concept.
To prove this, the researchers ran a massive experiment across 5 really diverse data sets. We're talking income prediction, diamond pricing, movie sentiment, and they tested 3 open-weight large language models. And they found something super interesting. Not all AI is built the same. GPT-OSS proved to be the best initial explainer, pumping out the most readable drafts, even though it still had a baseline error rate of over 22%. DeepSeek R1? Well, it was way too lenient. It was prone to over-accepting errors, which makes it a pretty terrible editor. But QN3? QN3 was the ultimate verifier. Its architecture just gave it the stable decision-making required to be an absolutely ruthless and accurate critic.
So the absolute crucial point is this number right here, 95.21%. When the researchers paired GPT-OSS as the explainer with QN3 as the verifier, the magic truly happened. Without a verifier, the explainer was only accurate about 77.8% of the time, but the two-stage framework rocketed that accuracy up to an incredible 95.21%. It successfully blocks 78.5% of all hallucinations and errors from ever reaching the end user. That is a game changer.
And we can actually track this improvement over time using something called the entropy production rate, or EPR. In simple, conversational terms, EPR just measures the AI's internal uncertainty and confusion. And as you can see, the moment the explanation goes through just 1 or 2 iterations of that refeed loop, the internal uncertainty drops sharply. The verifier's strict feedback literally stabilizes the explainer's reasoning. This proves that the framework isn't just a temporary band-aid. It actively forces the system to generate more coherent, more confident, and most importantly, correct outputs.
Which brings us to our final section, the trustworthy AI future, and how we democratize this technology.
Why does this matter so much for everyday users like us? Just look at the Flesch-Kincaid readability scores. If we give a user the raw XAI output, text analysis shows they need a read-in grade level of 21.79. That means you literally need a postgraduate degree to even comprehend why the AI made a decision. But once that data passes through our verified explainer verifier framework, the reading level drops to 12.94. It takes PhD-level data, translates it into super accessible everyday high school-level language. And crucially, that verification stage guarantees it doesn't lose a single drop of factual accuracy in the process.
And I want to leave you with this final, somewhat provocative thought. In a world that is increasingly governed by algorithms, from the healthcare treatments you receive to whether or not you can buy a house, shouldn't the right to a clear, honest explanation be universal? This brilliantly simple concept of AI checking AI proves that we really don't have to just accept the black box. We can actually force machines to explain themselves in our own language without lying to us. Thank you so much for joining me for this explainer. I really hope this helped you decode the future just a little bit better. See you next time.